Hey guys, and welcome to this tutorial where we're going to be solving all the exam questions on functions from the new specification in Edexcel. We'll be focusing on questions which relate to the domain, range, composite and inverse functions. At the end of the tutorial, we'll conclude on what you need to look out for, the related topics you need to study and the trends we've seen in previous years. For the questions, I'd encourage you to pause the video and try the questions yourself before seeing the solutions. So without further ado, let's get straight into it.
Okay, so the first question gives us this function g of x is equal to 2x plus 5 divided by x minus 3 for all values of x greater than or equal to 5. And the first part asks us to find g of 5. Okay, so you should be aware that this is called a composite function. Reason is because we are composing the function g of 5 into the function of g of x. So let's go ahead and do that. Now for composite functions, I always like to make use of square brackets. And you'll see while we're doing these calculations that it makes things a lot clearer. Okay, so let's first evaluate the inner function g of 5 by substituting 5 into g of x, which gives us g of 2 multiplied by 5 plus 5 divided by 5 minus 3. Evaluating what's inside the red brackets, we get that this is equal to g of 7.5. So now we need to substitute 7.5 into the function g of x, which is equal to 2 times 7.5 plus 5 divided by 7.5 minus 3. And evaluating this, we get that this is equal to 4.4 recurring for 2 marks. So the next part asks us to state the range of g, and this question is for 1 mark. Now, since we've been asked for the range, you can expect that we're going to produce an inequality which satisfies the range of values that g can take. I've seen many students see the fact that this is a 1 mark question and just assume they need to substitute the critical value of x they see and guess the direction of the inequality sign. I would strongly suggest that for questions where you have a rational function, you sketch the graph to see the behavior of your function on its domain, which is going to help you determine what your upper and lower bound is for the range. So let's go ahead and sketch the graph of g of x. Now, as I said, it's a rational function. Now, one thing you should know about rational functions is that when we have a degree of 1 in the numerator and the denominator, their graphs look similar to the graphs of reciprocal functions. Now, the way I go about sketching rational functions is start off with our x, y coordinate axis. We can work out the y-intercept by subbing x equals to 0 into the function, which gives us negative 5 over 3, which I've just plotted here. We can work out our x-intercept by setting this function equal to 0. And if you solve that equation, you get that x is equal to negative 5 over 2, which I've just plotted here. We now need to work out our asymptotes, which will serve as a guide to connecting these points and drawing the curve, which we already know looks similar to a reciprocal curve. So we know that a vertical asymptote exists where the function g of x is undefined, and that's where the denominator is equal to 0. So solving x minus 3 equals 0, we get that the vertical asymptote is where x is equal to 3. Now, to find the horizontal asymptote, we're going to use a special rule which we use when we have a rational function where the degree of the numerator is equal to the degree of the denominator. In this case, the degree of the numerator and denominator both equal to 1. So what we do to get the horizontal asymptote is we take the ratio of the leading coefficient between the numerator and the denominator. That's the leading coefficient of the polynomial terms with the highest degree. Okay, so in the numerator the coefficient is 2 and in the denominator the coefficient is 1. So taking the ratio, we simply do 2 divided by 1 to get that the horizontal asymptote is at y is equal to 2. So let's just update this on the diagram. So now we have our asymptotes and we've got the intercepts for the graph. Because we know what the shape should look like, we can use this as a guide to connecting the points
and drawing the curve. You can see how the curves have been drawn to tend towards the asymptotes but never touch them, okay? My bad if this one looks like it's touching the asymptote. It should never touch the asymptote, okay?
So now that we've sketched the graph, let's have a look at how the function behaves for different values of x on its domain. Now we know that domain is all values of x greater than or equal to 5. So that means that x equal to 5 is a critical value in this function. So subbing x equal to 5 into this function gives us that g of 5 is equal to 7.5. We actually calculated this earlier.
So let's first plot these points on the graph, 5 and 7.5. Since x is a critical value, it means that 7.5 is going to be one of our bounds for the range. But looking at what happens to the function for different values of x on its domain allows us to determine whether this bound is the upper bound or lower bound. Now we know that the domain is all values of x greater than or equal to 5. We can see that as we move to the right of 5 and x gets larger and larger, this curve actually gets smaller and smaller. So that tells us that 7.5 is actually an upper bound, and therefore we can say that g of x is less than or equal to 7.5. To find the lower bound, we can see that as x gets larger and larger, yes, the function is decreasing, but it does tend toward the y asymptote, which is equal to 2. So our lower bound is 2, and therefore the range of g are the values of y that are greater than 2. We're using a strict inequality here as y cannot be equal to the asymptote, as that's where it's undefined, but less than or equal to 7.5, okay? So that definitely felt like a lot of work for 1 mark, but the reason I'm showing you the sketching method is so that you avoid the mistakes that a lot of students make of just substituting values and guessing, but also because sketching the graphs helps you to easily see the upper and lower bounds for the range, especially for rational functions where these bounds are usually determined by your horizontal asymptotes, okay?
The last part asks us to find g inverse of x stating its domain. So to find the inverse of this function, assuming that it exists, we are going to use the swapping variables method. So we're going to let x be equal to y, and so swapping variables gives us that x is equal to 2y plus 5 over y minus 3. And now we have to solve for y. So let's multiply both sides by y minus 3, and this gives us x times y minus 3 is equal to 2y plus 5. Expanding out the brackets on the left side, we get that xy minus 3x is equal to 2y plus 5. Now we need to make y the subject of this equation. So let's do that by collecting the y terms. So if I subtract 2y from both sides of the equation and I add this 3x to both sides of the equation, I get xy minus 2y is equal to 3x plus 5. So we now have like y terms on the left side of the equation, and so we can factor out the y, giving us that y times by x minus 2 is equal to 3x plus 5. Dividing both sides of the equation by x minus 2, we get that y is equal to 3x plus 5 divided by x minus 2. And so now that we've solved for y after swapping the variables around, we've found g inverse of x. Now we're also asked to state the domain. Now you should be aware of this fundamental result that the domain of f of x is the range of the inverse function, f inverse of x, and the range of f of x is the domain of f inverse of x. So since we've already found the range of the original function g of x, using the bottom result, we can deduce that the domain of its inverse is equal to the range of the function. And therefore, we can conclude that the inverse of the function g inverse of x is equal to 3x plus 5 over x minus 2, where the domain is all values of x strictly greater than 2, but less than or equal to 7.5, okay? In this question, we're given the function f of x is equal to 2x squared plus 4x plus 9,
for all real values of x. The first part asks us to write f of x in the form a times by x plus b all squared plus c, where a, b and c are integers to be found. To get f of x into this form, we need to complete the square. And so assuming you know how to do this, I'm just going to write the equivalent of this function in complete square form to get our first 3 marks. 2 times x plus 1 all squared plus 7. The next part of the question says sketch the curve with the equation y is equal to f of x, showing any points of intersection with the coordinate axis and the coordinates of any turning point. You should already be aware that writing a quadratic polynomial in complete square form provides a handy way of sketching the graphs. We can work out the y-intercept by subbing x equals to 0, giving us 0 plus 1 all squared, which is 1, times by 2, which is 2, plus 7, which gives us 9, which we can just plot here. We can also deduce the turning point from the complete square form. To find the x coordinate, we need to work out the value of x that makes this bracket equal to 0, which is clearly minus 1. And we always take the number outside of our brackets as the y coordinate, giving us that the coordinate of the turning point is minus 1 and 7, which I've just plotted here. Looking at the coefficient of our x squared term, we can see that this is a positive number. And that means that the shape of our curve will be a smiley face. And therefore, this turning point that we've just found must be the minimum point of our function. And so therefore, we can draw the curve as follows. Notice that this function has no roots. In other words, it doesn't cross the x-axis. And you can double check this by setting the function equal to 0 and trying to solve for x. You'll see that you cannot solve the equation for x because there's no values of x in the real plane that would satisfy that equation, and so there are no roots to this equation, which just validates what we see here. Okay. The next part asks us to describe fully the transformation that maps the curve with the equation y is equal to f of x onto the curve with the equation y is equal to g of x, where g of x is equal to 2 times by x minus 2 all squared plus 4x minus 3 for all real values of x. Now, there are a couple of ways of doing this. One way is by attempting to sketch the graph of g of x and working out the transformation from f of x onto g of x. Another way to look at this is to simply ask yourself, well, what's the difference between f of x and g of x? And is there a way that we can express g of x in terms of f of x? Because if we can do this, then we can directly see the operations that we need to perform to transform f of x onto g of x. Now, on inspection, we can see that the functions are actually quite similar. In both cases, we have a leading value of 2. For this function, we have x squared, and then for g of x, we have x minus 2 squared. So we also have the term 4x appearing in both functions.
So we can see the functions are similar but not the same. The question is, what is a possible transformation that can map f of x onto g of x?
The real clue in this question is here, where we have x minus 2, which looks like it may have been composed inside of the function f of x. So given that we know that f of x is equal to 2x squared plus 4x plus 9, we can make an educated guess that we could get g of x by subbing x minus 2 into the function of f of x. Let's try and see what the function f of x minus 2 looks like once we compose x minus 2 into the function of x. How we would do this is we would simply replace the x terms for x minus 2. And so expanding this bracket, we get that this is equal to 2 times x minus 2 all squared plus 4x minus 8 plus 9. And so simplifying, we get that this is equal to 2 times x minus 2 all squared plus 4x plus 1. So comparing f of x minus 2 with g of x, This expression is equal to this expression, and that's why I intentionally chose not to expand this bracket. We also have plus 4x in both functions. The only difference is this minus 3 and 1. And so in order to map this function f of x minus 2 onto g of x, we need to subtract 4. And therefore, g of x is equal to f of x minus 2 minus 4. And so now we've been able to write g of x in terms of f of x. We can see that the translation would involve moving all of our x coordinates 2 units to the right because we have x minus 2, and moving all of our y coordinates 4 units down because we have minus 4. And therefore, the transformation that maps the curve f of x onto g of x can be described by translating in the vector 2 minus 4. Okay. The next part asks us to find the range of the function h of x is equal to 21 over 2x squared plus 4x plus 9 for all real values of x. Now the first thing we might try to do is sketch the graph, but seeing that this is a function of the form 1 over x squared, well, that seems like it could be a little bit trickier. Now for range questions, if you find it hard to sketch the graph, you need to try and find some mathematical or logical way of deducing the maximum and minimum values of the function. Now notice that the denominator is equal to our function f of x. So we can write that h of x is equal to 21 over f of x. Now since this is a fraction, we can say that h of x is going to be maximum when our denominator f of x is minimum. Now we know from part B that f of x is minimum when y is equal to 7, and therefore the maximum value of h of x is equal to 21 divided by 7, which is equal to 3. Now when trying to deduce the minimum of a function, try to work out whether the range is strictly positive. Looking at the function, we have a positive number in the numerator, and by looking at the complete square form of our denominator, which is 2 times by x plus 1 all squared plus 7, well, x plus 1 all squared is going to be positive for all real values of x. And if we multiply that by 2, we get a positive. And if we add by 7, we also get positive. So therefore, this function will remain positive for all values of x. And so the range of h of x satisfies this inequality where h of x can take all values strictly greater than 0 but less than or equal to 3. Again, you always need to double check whether your inequality is strict or not. We know that the range cannot be equal to 0 since the numerator is equal to 21, which is a non-zero value. So figure 4 shows a sketch of the graph y is equal to g of x, where g of x is equal to x minus 2 all squared plus 1 for values of x less than or equal to 2, and 4x minus 7 for values of x strictly greater than 2. Part A asks us to find the value of gg of 0, and this question is 2 marks. So first of all, we can see that g of x is a piecewise function, which is basically a function that it's made up of multiple subfunctions. And you can see that this is illustrated quite nicely on the diagram, which we can call g of x. On the left, we have our quadratic function for values of x less than or equal to 2. And for all values of x strictly greater than 2, we have this linear function 4x minus 7, which would be to the right side of this point 2 here. Okay? In order to find gg of 0, we first of all need to evaluate the inner function, which is the function of g evaluated at 0. It's important to look at the domain in order to determine which subfunction we need to substitute our value into. Now, as x equal to 0 is less than 2, then this is a subfunction that we need to substitute x is equal to 0 into. X minus 2 all squared plus 1.
Okay, so gg of 0 is equal to g of 0 minus 2 all squared plus 1. And calculating the value inside of the square brackets, we get that gg of 0 is equal to g of 5. Now to finish off this question, we need to evaluate the function of g at 5. Looking at our domain, since 5 is a value of x which is greater than 2, it means that we need to substitute 5 into this function, and therefore g of 5 is equal to 4 times by 5 minus 7, which is equal to 13. Part B of this question says find all the values of x for which g of x is strictly greater than 28, and this is a 4-mark question. Now let's take a step back and think about this visually first, because by asking us to find all the values of x for which g of x is greater than 28, this question is asking us where is the region where the graph or the function is greater than 28, and what are the x values that produce that region. Now earlier on I mentioned that this point here is clearly going to be the point 2. Now why? Well, it's quite clearly the point where the piecewise function changes from a quadratic curve to a straight line, and can be confirmed by looking at the domain. Okay, now if we were to work out the corresponding y value of x is equal to 2, well, because x is only allowed to be equal to 2 when we're looking at this function, the quadratic, so we'll have to substitute x equal to 2 into this function to give us 2 minus 2 all squared, so 2 minus 2 is 0, all squared is 0, plus 1. So that gives us a corresponding y value of 1. The reason why I've done this is because I just want to get a feel for where the value 28 is on this graph. Okay, so since this is 1, we can assume that 28 is somewhere quite well above 1. Okay, so as I mentioned before, we're trying to figure out the region or the x values that give me y values which are greater than 28. Okay, now if we map this value of y is equal to 28 back onto the graph, there would be two corresponding x values, one here and one here, showing that there are two x values when y is equal to 28. But we're not after the x value where y is equal to 28, because we've been asked to find the x values where y is greater than 28. And y is greater than 28 at these points in the function, here and here, which would be produced by x values as shown in the diagram. So these points would still be important for us because they're going to act as bounds for what we can visually see as a disjointed set of x values. Please note that for the purpose of explaining this to you, I have drawn these intervals with a closed circle, but because we're looking for where the function is strictly greater than 28, this should be drawn with open circles. Okay, so what we need to do to solve this problem is find the set of these x values that satisfy this inequality. Let's go ahead and start with this set. So we can find out this set by working out where the quadratic function is greater than 28. In other words, where x minus 2 all squared plus 1 is strictly greater than 28. Now, solving quadratic inequalities aren't always as straightforward because it's important you know the region that you're looking at, but we've already done the hard work in deducing where that region would be. It would be all values to the left of this critical point. So let's figure out the critical point or the critical value by setting this as an equation. Okay, so instead let's solve this as an equation. X minus 2 all squared plus 1 is equal to 28. Subtracting 1 from both sides, we would get x minus 2 all squared is equal to 27. If we take the square root of both sides, we'll get that x minus 2 is equal to plus or minus the square root of 27. And if we add 2 to both sides of the equation, we get that x is equal to 2 plus or minus the square root of 27. Now, this critical value is clearly on the negative x-axis, and therefore 2 plus the square root of 27, we can exclude that as a value, as that's a positive number. Instead, we'll use 2 minus the square root of 27, but I'm still going to double check that this is indeed a negative number, as you should always be looking to double check in your exam. Okay, So let's just type in 2 minus the square root of 27 and press the SD button. And that's equal to a negative value, okay? Therefore, we can conclude that the critical value is equal to 2 minus the square root of 27. And let's just update this on the diagram. So now we have our critical value. We can deduce that the set of x values which satisfy this inequality on this side is the set of x values strictly less than 2 minus the square root of 27. Now let's work out the other set of values, and this can be found by solving the following inequality. 4x minus 7 is greater than 28. We can solve this right away by adding 7 to both sides, giving us the 4x is greater than 35, and if we divide both sides of the inequality by 4, we get that x is strictly greater than 35 over 4, giving us the other set of values that satisfy this inequality. And I'll just add 35 over 4 to this diagram just to complete everything. And now we have both of our disjointed sets. We can conclude that therefore the set of x values that satisfy this inequality is the set of x values less than 2 minus the square root of 27. And because they are disjointed, we must use the word or. The set of x values strictly greater than 35 over 4. The next part of the same question says that the function h is defined by h of x is equal to x minus 2 all squared plus 1 for values of x less than or equal to 2. Part C asks us to explain why h has an inverse but g does not. And this is a 1-mark question. We already know that this is the function g of x, and h of x has been defined to be the quadratic function x minus 2 all squared plus 1 only for values less than or equal to 2. So that would be represented by this portion of the graph. Okay, and we'll just put 2 here. And let's just label this y is equal to h of x. All right, so the question is, why does h have an inverse but g does not? Well, in order for a function to have an inverse, it must be a one-to-one function or mapping. And you can test if a function is one-to-one by simply conducting the horizontal line test, which means that if you're able to draw horizontal lines going all the way through your graph, and there's only one point of intersection between the graph and the lines you've just drawn, then that means that it's a one-to-one function and therefore has an inverse. So h has an inverse because it's a one-to-one function. However, g does not, because if we extend these lines, we'll see that there are more than one point of intersection between the graph g of x and the horizontal lines we've just drawn. Okay, so here we have 2 points of intersection, here we've got another 2 points, etc. Okay, so the reason why h has an inverse but g does not is because h is a one-to-one function, but g of x is a many-to-one function. Okay, part D says solve the equation h inverse of x is equal to negative a half, and this is for 3 marks. So in order to solve this equation, we need to find a way of making x the subject of this equation. So some of you might remember that if you have a function, say f of x, and it has an inverse, the way to find x is to apply its inverse to itself. Okay, so using this fact here, if we apply h to both sides of this equation as follows, we would get h of h inverse of x is equal to h of negative a half. We've just seen that this side would be equal to x, and all we have to do now is evaluate the function h at negative a half. So substituting negative a half into this function h of x, we are going to get x is equal to negative a half minus 2 all squared plus 1. And evaluating this term, negative a half minus 2 is equal to minus 5 over 2, and therefore we get x is equal to minus 5 over 2 all squared plus 1. And evaluating this term, we get that x is equal to 7.25.
So in this question, we're given that the function f is defined by f of x is equal to 3x minus 7 over x minus 2 for all real values of x, where x is not equal to 2. And the first part asks us to find f inverse of 7. Now one way we could solve this is by using the swapping variables method to work out the inverse function of f of x and then substitute 7 into that function. However, I'm going to solve this using this result, that the range of f of x is the domain of f inverse of x. Now in this case, the range of f of x is going to be all of the outputs of the function f of x, which is 3x minus 7 over x minus 2, where x is valid. And the domain of the inverse, well, these are simply all of the values that we can input into the function f inverse of x, including the number 7.
So using this result, we can say that the range of the function 3x minus 7 over x minus 2 is equal to 7, which is the domain of the inverse. And by working out the value of x, which makes this expression equal to 7, we get f inverse of 7. And now we have this equation, we can work this value of x by simply solving this equation for x.
So let's go ahead and solve this equation. So multiplying both sides by x minus 2, we get that 3x minus 7 is equal to 7 times x minus 2. Multiplying the brackets on the right side, we get 3x minus 7 is equal to 7x minus 14. If we subtract 3x from both sides and add 14 to both sides, we get that 7 is equal to 4x. And dividing both sides by 4, we get that x is equal to 7 over 4. And so therefore, f inverse of 7 is equal to 7 over 4. Okay. The next part asks us to show that f of x is equal to ax plus b over x minus 3, where a and b are integers to be found. So here is a composite function, and I'm going to make use of these square brackets to make things clearer. So we need to substitute what's in these square brackets inside of our function f of x. That happens to be f of x itself. So we get the following: 3 times by 3x minus 7 over x minus 2 minus 7, all divided by 3x minus 7 over x minus 2 minus 2. Expanding the brackets in the numerator, we get 9x minus 21 over x minus 2 minus 7, all divided by 3x minus 7 over x minus 2 minus 2. I'm now going to subtract the algebraic fractions in the numerator and the denominator. Assuming you know how to do this, we get the following: 9x minus 21 minus 7 times x minus 2 over x minus 2, all divided by 3x minus 7 minus 2 times by x minus 2 over x minus 2. You can get the common denominator of x minus 2 by seeing this term 7 as 7 over 1 and the 2 as 2 over 1 and multiplying the top and bottom of those fractions by x minus 2 and dividing this fraction by this fraction. You should notice that the expression x minus 2 will cancel, giving us 9x minus 21 minus 7 times x minus 2 all over 3x minus 7 minus 2 times x minus 2. Expanding out the brackets, we get 9x minus 21 minus 7x plus 14, all divided by 3x minus 7 minus 2x plus 4. Okay. Next, we simplify the fraction by collecting the like terms, giving us that this is equal to 2x minus 7 over x minus 3. So looking at this, we can see we now have f of x in the form ax plus b over x minus 3, where a is equal to 2 and b is equal to minus 7. Okay. This question gives us figure 2, which shows a sketch of a curve C with the equation y is equal to f of x, where f of x is equal to 4 times x squared minus 2 times by e to the power of negative 2x for all real values of x. So the first part asks us to find the derivative of the function f prime of x and show that it's equal to 8 times by 2 plus x minus x squared times by e to the power of negative 2x. The next part then says, hence find in simplest form the exact coordinates of the stationary points of C. So as we're interested in the range part for this question, we're just going to quickly skim through the answers for part A and part B. For A, you would use the product rule to show that f prime of x is equal to this function. In order to calculate the exact coordinates of the stationary points, you would set this function equal to 0 and solve x, which would give you two stationary points. The first one would be minus 1 minus 4e squared. You would get the y coordinate by simply subbing your x coordinate into the original function. And the second stationary point would be 2 and 8 times e to the power of negative 4.
So for the next part, we're told that the function g and the function h are defined by g of x is equal to 2 f of x for all real values of x, and h of x is equal to 2 f of x minus 3 for all values of x greater than or equal to 0. Now part ci asks us to find the range of g. So we already have a graph of the function f of x. And since we have stationary points, it makes sense to use these stationary points to work out the range of f of x or any transformation of f of x. And g of x, we can see, is a transformation of f of x. So to visualize this, let's start off by just plotting the y coordinates of our stationary points on the graph. This here is clearly one of our stationary points, and that's where our x value is negative, and so this y coordinate must be minus 4e squared, and this here is also clearly a stationary point, and it's when our x coordinate is positive, so the y coordinate here must be 8e to the negative 4. Now looking at this graph, we can see that
this point with y coordinate minus 4e squared must be the lower bound for f of x.
This one wouldn't, because you can see that the curve goes through this point, okay? So we can say that when x belongs to the set of real values, f of x is greater than or equal to negative 4e squared. And since we know that g of x is equal to 2f of x,
well, that's just the transformation of the graph f of x where all the y coordinates are multiplied by 2, and therefore g of x must be greater than or equal to 2 multiplied by negative 4e squared, and therefore g of x must be greater than or equal to negative 8e squared. Part Cii asks us to find the range of h. Now we see that h is also a transformation of f of x. However, the domain of h is restricted to all positive values of x greater than or equal to 0. So let's use a critical value of x equal to 0 to determine one of the bounds for this range. And we do that by subbing x equal to 0 into the function h of x. So h of 0 is equal to 2 times f of 0 minus 3, which equals 2 times by 4 times 0 squared minus 2 multiplied by e to the power of negative 2 times 0, all minus 3. We mustn't forget the negative 3. Evaluating the bracket, we get 2 times by negative 8 times 1 minus 3, and that's equal to negative 19. So negative 19 is one of our bounds. Now to determine whether this is an upper or lower bound, let's have a look at the other bound. Now we know that for the function h of x, our domain is restricted to all positive values of x, which is this region. And this means that the y coordinate for the stationary point in this region, which is 8e to the power of negative 4, is going to help us find the other bound. Now we know that in this region, when x is greater than or equal to 0, we have that the range of the function f of x is less than or equal to 8e to the negative 4.
That's the point we just discussed.
And as h of x is also a transformation of f of x, we need to perform some arithmetic on this inequality to work out the range of h, as we did previously. So, given that h of x is equal to 2f of x minus 3, we need to multiply the upper bound of f of x by 2 and then subtract it by 3. So the range would satisfy this inequality where h of x is less than or equal to 2 multiplied by the bound we found, 8e to the negative 4 minus 3. Okay? Working out the right hand side, we get that h of x is less than or equal to 16 times e to the negative 4 minus 3. So based on this inequality, we can see that 16e to the negative 4 minus 3 is going to be the upper bound for the range of x. And so that means that negative 19 must be the lower bound for the range of x. You can also work out this value in your calculator and see that this is equal to minus 2.70 and so on, which is greater than negative 19. So that again shows you that this would be the upper bound of this inequality. And so the range of h satisfies this inequality where h of x take all values greater than or equal to 19 but less than or equal to 16e to the negative 4 minus 3.
In this question, we're told that the function g is defined by g of x is equal to 3 ln x minus 7 over ln x minus 2 for values of x greater than 0, where x does not equal to k, where k is a constant. Part A asks us to deduce the value of k. So g of x looks like a rational function, and you should know that for rational functions, the domain is always restricted for values of x, which would cause the denominator to be equal to 0, because that's where the function is undefined. So g of x is undefined when ln of x minus 2 is equal to 0. So to find this value of x, all we need to do is solve this equation. If we add 2 to both sides, we get ln x equals to 2. And taking the exponential of both sides, we get e to the power of ln x is equal to e to the power of 2. The left hand side is equal to x, and therefore x is equal to e to the power of 2. So now we found the value of x that makes the function undefined. We can deduce that k is equal to e to the power of 2. The next part asks us to prove that g prime of x is greater than 0 for all values of x in the domain of g. Now I'm going to quickly skim through this part. Since g of x is a rational function, it's best to use the quotient rule to differentiate this function, and you would get g prime of x is equal to 1 over x times by ln of x minus 2 all squared. And when x is greater than 0, 1 over x, which is part of this function, will be greater than 0, and 1 over ln of x minus 2 all squared must be greater than 0. So their product must be greater than 0, and therefore g prime of x is greater than 0 for all x in the domain. The last part asks us to find the range of values of a for which g of a is strictly greater than 0. Now we know that g of x is equal to 3 ln x minus 7 over ln x minus 2. To find the values of a that satisfy this inequality, we need to solve the following inequality. 3 ln a minus 7 over ln a minus 2 is strictly greater than 0. Now you need to be careful when you're solving inequalities with algebraic fractions or rational functions. The first thing you need to do is determine your critical points. We know that this function is equal to 0 when our numerator is equal to 0. So we can get our first critical point by setting the numerator 3 ln a minus 7 equal to 0 and solving for a. The second critical point would be where the function is undefined, and that's when the denominator is equal to 0. So we get the second critical point by solving the equation ln of a minus 2 equals to 0. So solving the first equation, if we add 7 to both sides, we get that 3 ln of a is equal to 7.
If we divide both sides by 3, we get that ln a is equal to 7 over 3. And taking the exponential of both sides, we get e to the power of ln a is equal to e to the power of 7 over 3. And as this left-hand side is equal to a,
we get that a is equal to e to the power of 7 over 3.
which is one of our critical points. The other critical point is found by solving equation number 2. So adding 2 to both sides, we get that ln a equals 2. Taking e to the power of both sides, we get e to the power of ln a is equal to e to the power of 2. And therefore, a is equal to e to the power of 2, our other critical point. So let's draw these points on a number line. E to the power of 2 is less than e to the power of 7 over 3. And because we're solving a strict inequality, I'm going to use open circles to illustrate the points on the number line. Now, to find out which region satisfies this inequality, we need to see which values between or beyond these critical points that give us a positive function when we sub those values into the function.
So if we sub in any value which is less than e to the power of 2 into this function, we would get a positive. Let's just test that by subbing in 2, which is less than e to the power of 2. We get a positive value. Let's use a lower number. We also get a positive number. So this region would work. If we did the same thing for any value between e to the power of 2 and e to the power of 7 over 3, we would get a negative output. Doing the same for any value greater than e to the power of 7 over 3 would give us a positive output. So the regions that would satisfy this inequality are as illustrated. However, based on the domain that we were given for g of x, any values of a must be greater than 0. And therefore, the range of values of a that satisfy the inequality are all values of a strictly greater than 0, but less than e to the power of 2, or a greater than e to the power of 7 over 3. Okay?
For this question, we're told that the functions f and g are defined by f of x equals 7 minus 2x squared for all real values of x, and g of x is equal to 3x over 5x minus 1 for all real values of x, where x does not equal to 1 over 5. The first part asks us to state the range of f. So to state the range of f, let's sketch the graph of f of x on the coordinate axis. So here we can see that our x squared coefficient is negative, and therefore it's going to be a sad face. We can work out the y-intercept by setting x equal to 0, which gives us 7. And we can also work out the roots of this function by setting it equal to 0 and solving for x. If you do that, you'll get that your roots are 1.87 and so on, or negative 1.87 and so on. So now we've sketched the graph, you can see that the upper bound for the range would be 7, and therefore the range would be values of f of x less than or equal to 7. The next part asks us to find gf of 1.8. So just writing this with square brackets shows us that we need to evaluate the function of f at 1.8 first, our inner function, and this gives us g of 7 minus 2 times by 1.8 squared when we sub this 1.8 into this function. Working out what's inside the red brackets, we get g of 0.52. Next, we need to evaluate g at 0.52 by subbing this
into this function, and this is equal to 3 times by 0.52 divided by 5 times 0.52 minus 1. Working this out in your calculator will give you an answer of 0.975. Okay. The last part asks us to find g inverse of x. So assuming this has an inverse, we can work this out using the swapping variables method. So if we let x equal to y, then we can say that x is equal to 3y over 5y minus 1. Multiplying the 5y minus 1 by both sides of the equation gives x times 5y minus 1 is equal to 3y. Expanding the brackets on the left hand side gives us 5xy minus x is equal to 3y. Now we need to collect the y terms, as we need to isolate the y to solve the equation. So I'm going to subtract both sides by 3y and add x to both sides. That gives us 5xy minus 3y is equal to x. We can now factorize this expression as follows. Y times by 5x minus 3 is equal to x. And so now dividing both sides of the equation by 5x minus 3, we get that y is equal to x over 5x minus 3. And therefore, g inverse of x is equal to x over 5x minus 3. For the last question, we're told that the function f is defined by f of x is equal to 8x plus 5 over 2x plus 3 for values of x strictly greater than minus 3 over 2. And the first part asks us to find f inverse of 3 over 2. So like we saw in a previous exam question, to find the inverse of f evaluated at 3 over 2, we're going to use the result that the range of f of x is equal to the domain of its inverse. So given that this is an expression for the range of f of x, and this is the value we are inputting into the domain of its inverse, we can set these equal and solve for x to find f inverse of 3 over 2. So if we cross multiply, we get that 2 times by 8x plus 5 is equal to 3 times 2x plus 3. Expanding the brackets on both sides, we get that 16x plus 10 is equal to 6x plus 9. Subtracting both sides by 6x and subtracting 10 from both sides, we get that 10x is equal to negative 1, and therefore x is equal to minus 1 over 10. So therefore the inverse of f at 3 over 2 is equal to minus 1 over 10. The next question asks us to show that f of x is equal to a plus b over 2x plus 3, where a and b are constants to be found. Now the answer to this question is 4 minus 7 over 2x plus 3, where a is equal to 4 and b is equal to minus 7. You can check out one of my previous tutorials to learn how to convert improper algebraic fractions, where the degree of the numerator is equal to the degree of the denominator, into mixed algebraic fractions of this form. Okay. Next, we're told that the function g is defined by g of x is equal to 16 minus x squared for values of x greater than or equal to 0 but less than or equal to 4. And we're asked to state the range of g inverse. Now, we've already been given the domain of the function g of x. So using the first result, that the domain of f of x is equal to the range of f inverse of x, well, that means that the range of the inverse is equal to the domain of the original function. And therefore, g inverse of x is greater than or equal to 0, but less than or equal to 4. The last part of the question asks us to find the range of fg inverse, and this is for 3 marks. Now, it's by no mistake that we've previously been asked to state the range of g inverse, which we found to be values between 0 and 4. Here we can see we've been asked to find the range of a composite function. So if you were working out fg inverse, what you would do is you would typically substitute the output values of g inverse into f. Now we know the possible set of output values are between 0 and 4. So that gives us the domain of our function of f. And so we can work out the range by sketching the graph of f evaluated at values of x between 0 and 4. So let's go ahead and do that. So firstly, we see that this is a rational function. So on the coordinate axis, let's first of all work out our intercepts. Our y-intercept would be the value of the function when x is equal to 0, which is equal to 5 over 3. Our x-intercept would be the value of x when the function is equal to 0, which if you worked it out, you would get minus 5 over 8. We can find our vertical asymptote by setting the denominator equal to 0 and solving for x to give us that the vertical asymptote is x is equal to negative 3 over 2, which we've just drawn here. Now, since the numerator and the denominator of the rational function have the same degree, it means that we can work out the horizontal asymptote by taking the ratio of the leading coefficients of the numerator and denominator. So if we do 8 divided by 2, we get a horizontal asymptote at 4, which we can just update on the graph. So now we've got our asymptotes and the intercepts, we can connect these points and draw the curve as follows. And so now we've drawn the graph of f of x. And in order to find the range, we need to determine the bounds of this function between 0 and 4. Okay? So if we take these as critical values, it means that we need to substitute this into our function to get the corresponding bounds for the range. So subbing 0 into our function, we get 8 times 0 plus 5 over 2 times 0 plus 3, which is equal to 5 over 3. And subbing 4 into the function, we get 8 times 4 plus 5 divided by 2 times 4 plus 3, which is equal to 37 over 11. So now we've calculated our bounds, we need to see which is the upper and which is a lower bound. In this example, it's very easy because 37 over 11 is greater than 5 over 3, and therefore 37 over 11 is the upper bound and 5 over 3 will be our lower bound. We could have also used the graph to help us see this, because the corresponding y value of 4, which we calculated to be 37 over 11, would be higher than the corresponding y value of 0, which we calculated to be 5 over 3. And so therefore the range of FG inverse satisfies this inequality, where it takes values greater than or equal to 5 over 3, but less than or equal to 37 over 11. And notice that these are non-strict inequalities because the domain that we used were non-strict inequalities. Okay. When solving exam problems which relate to the range of a function, these are the questions you should be asking yourself. Firstly, can you sketch the graph? If so, what's the behavior of the function for different values of x? Are you able to use any of the critical values in the domain to help you find out what the upper and lower bound is in the range? And if you can't sketch the graph, can you deduce anything about the range using mathematical or logical reasoning? For example, is the function only positive? Just for general tips, I would recommend you double check your inequality signs for your ranges and use square brackets for composite functions as we did in the previous questions. The topics that are related based on the previous exams are mapping. So for example, understanding what a one-to-one mapping is and how it's a necessary condition for a function to have an inverse, graph transformations, solving inequalities, and differentiation. The trends we've seen from previous exams is that these are typically 1 to 3 mark questions, and the popular functions they like to use are rational functions and quadratics. So I would definitely learn how to sketch these graphs. And finally, the fundamental result we discussed earlier. Okay, so I hope that was useful for you. Keep up the great work and we'll see you in the next tutorial. If you like this video, please give us a thumbs up, leave your comments down below, and subscribe to this channel so you'll be the first to know when we release our next videos.